You've heard of uranium. It powers nuclear plants. It fueled the atomic bomb. It's one of the most talked about elements on the entire periodic table. But there's another element sitting quietly just 2 spots away. Atomic number 90. Heavier, more abundant, and according to some scientists, potentially far superior as a nuclear fuel. Its name is thorium, and almost nobody is talking about it. So today, we're asking the question that nuclear engineers have debated for decades. Which is actually better for nuclear energy? Uranium or thorium? The answer might completely change how you think about the future of power. Let's start with the basics. Both uranium and thorium are heavy radioactive metals found naturally in the Earth's crust. Uranium has an atomic number of 92. Thorium sits at 90. They're neighbors on the periodic table, but their differences are dramatic. Thorium is actually 3 to 4 times more abundant than uranium on Earth. It's found in greater quantities, in more countries, and is easier and cheaper to mine. If abundance alone decided the winner, thorium would win instantly. But here's where it gets complicated. Thorium by itself is not fissile. That means you can't just drop it into a reactor and expect a chain reaction. Uranium-235 is naturally fissile. Split it with a neutron, and it releases enormous energy immediately. Thorium needs a head start. It must first absorb a neutron and transform, through a 2-step decay process, into uranium-233, which is fissile. Think of thorium as a fuel that needs a spark. Uranium is the spark itself. So why would anyone bother with thorium at all? Because once that conversion happens, the advantages stack up fast. Thorium reactors produce significantly less long-lived radioactive waste than uranium reactors. Uranium waste remains dangerous for tens of thousands of years. Thorium waste? Hundreds of years. That's a staggering difference when you're talking about underground storage facilities and generational responsibility. There's another critical advantage. Thorium is extremely difficult to weaponize. The uranium-233 produced in a thorium reactor is contaminated with uranium-232, which emits intense gamma radiation. That makes it nearly impossible to handle covertly for weapons purposes. Uranium-235 and plutonium, byproducts of conventional uranium reactors, have a dark history of being diverted for weapons programs. Thorium changes that equation entirely. And then there's meltdown risk. Traditional uranium reactors require active cooling systems. If those systems fail, you get Chernobyl, you get Fukushima. Thorium molten salt reactors, the most promising thorium design, are fundamentally different. They operate at atmospheric pressure. If something goes wrong, the reactor passively shuts itself down. No explosion, no meltdown. The physics itself acts as the safety mechanism. So why aren't we already running on thorium? The answer is history. In the 1950s and 60s, the United States had a working thorium molten salt reactor at Oak Ridge National Laboratory. It ran successfully for years, but governments chose uranium, partly because uranium reactors produced plutonium useful for nuclear weapons during the Cold War arms race. Thorium couldn't offer that, so it was shelved. Not because it failed, because it wasn't useful for bombs. Today, countries like India, China, and Norway are investing heavily in thorium research. India, in particular, has enormous thorium reserves and a serious national program to make it work at scale. Uranium built the nuclear age we know, but thorium might define the nuclear age we need. More abundant, cleaner waste, harder to weaponize, safer by design. The only question is whether the world is finally ready to give it the chance it never got.